Oh, the internet. Good morning and good afternoon, everyone. Welcome to Taylor Hobson webinar series. My name is Alice, and I'm working as a digital marketing specialist at Taylor Hobson. And today we'll have our application engineers, TJ, to do a webinar on the latest features of our PGI Optics software. As you may know, our PGI Optics software has been used on our optics product range, and it has been used by a lot of optics manufacturers to analyze their optical parts. So at the end of the webinar, we'll have our business development manager, Neil Fitzgibbon, to join our to answer all your questions. So please feel free to submit your questions. Use the Q&A section. Now I'm going to ask TJ to join us, and I will see you all in a bit.
Hi, thank you for joining me today on this webinar on 2D measurements with the PGI Optics software. This will be a 20 to 30 minute presentation with a Q&A session in the end. If you have any questions, please feel free to submit them on screen and I'll answer them at the end. The PGI Optics software is a software specific for our optics range of instruments, designed specifically for the optics industry. It has a new simple to use interface that's set to reduce operator error, save time, and give administrative specific control. It revolves around being able to take measurements directly from optical prescriptions and getting analysis directly from there. And with this software, we need only enter the optical prescription, and the software will generate the path for the stylus, detect the possibility of flanking, gauge collision, which can prevent downtime. The interface for the PGI Optics software has a home screen for operator, then an unlock button to get to the programming administrative side of it. On the operator side, there are a few basic controls: return to the previous page, unlock to get to the admin side, manual control where we can take measurements and measurements of parts, and joystick, then settings and an integrated help menu. The main tools used are the joystick control. You can click and hold to move the system, move to position, contact, manually crest the part, change your speeds, and move set distance. We have the manual control, which is where all of our measurements, manual measurements, part measurements, and calibrations occur. And we now have a built-in help file with instructions, step-by-step instructions on how to take measurements using the PGI Optics software. Start off with the standard measurement. This being a PGI system, you always have the ability to take a standard measurement whether you know anything about the part or not. This means you can just type in a set length and trace away. So you can use this for non-optical parts, for tooling or other metal manufactured parts. You can also use this on optics that you don't know the prescription of, and for example, send them to Talymap for roughness analysis, or send them to AEU to derive the optical prescriptions or the spherodifractive prescriptions. And in here you can set measurement length, change your data spacing, change your speed, and move back to the start position if you want to take a series of measurements sequentially. With the PGI Optics software, both the measure and all of our measurement options, we get a live preview of our trace. So as we start collecting data, we see the trace on screen, so we get live feedback to what we're measuring, which is particularly helpful if we're measuring parts that we don't know the prescription for. And we have the measure part. So this uses a predefined part, and we'll go into the part definition setting up programs later in this presentation. But here we can choose the parts that we have programmed, choose how we want to crest these components, whether we want to crest for the first angle, or if we have good enough tooling that we don't need to crest. And then we have our options for where we want to analyze the data. You can choose to analyze directly in the PGI Optics software, so everything remains on one page. We can also use the familiar AAU, Aspheric analysis utility, and we can also use Talymap for some additional analysis. When we use the measure part, we've entered the prescription of this optic, and now the stylus will automatically measure from the start to the end of the component, automatically measuring end to end, accounting for the arcing motion of the stylus. This creates a perfectly balanced measurement, so the Z height where it starts is the same Z height where the measurement ends. And so after the crest on the component, it'll automatically move to the start position, trace till it ends, and this precise control allows us to measure optics, the full clear aperture of optics, even on very small millimeter-sized clear aperture optics. And this also allows us to ensure that our stylus won't flank or the gauge body won't crash in our optic, since we'll check for that. It'll automatically check for that ahead of time. A feature of this measure part is the immediate remeasure. So once we've taken a measurement, we can immediately remeasure and it'll remeasure the same optic. What this is, this was implemented based on customer feedback, where there were customers that were measuring many of the same part in a row. And so they want to take off a part, put a duplicate one on, and immediately remeasure without needing to recrest. With good fixturing, this is possible. Take your measurement, remove the part, put a new part in on the same fixture, immediately remeasure, and then we get quick results. I have it shown here, held on through jaw chuck. You can also, depending on your manufacturing process, have it held in a collet for very repeatable measurement location. Once we've done our measurement, we're able to see the raw data of the part, the raw prescription, the raw optical profile of the trace, along with the coordinates it was taking, and then the amplitude. And then we can see the residual data after the analysis is played through. So this is with the form removed. Here is the residual data, and then all the corresponding parameters, which is our base radius, our profile total, the tilt of the component, the slope, etc. And here we also have the ability to mask specific regions. So say there was an asperity or an object or something that didn't belong on the trace, we can mask that out and reanalyze. In this case, the trace has gone off of the surface, and so that portion could be masked. With a PGI optic system equipped with a rotary stage, such as our matrix freeform or a standard PGI optics with a rotary stage, we have the ability to take multiple traces on the part, on an aspheric part, in a spoke-like manner, such as we see in this sketch, where we take a trace, part rotates, take another trace, part rotates, take another trace. And when we get our results, we can see the results from angle 1, 2, 3, for as many angles as we've included, an average of those 3, and then all of them overlapped. A recently added feature is now we can look at those spoke traces in a 3D image where they're all combined into a 3D surface. And so we can look at non-rotationally symmetric errors through a 3D map, and we have our surface parameters, our S parameters, displayed. In the manual control in the operator interface, we have calibration built in. Calibration is a fully automatic one-hit routine where we need to select the stylus, select our calibration ball, tell it to contact and crest, and go ahead and measure. We just select our stylus and measure, and we'll automatically get a calibration. The software treats this just like any other optic, where it predicts the largest trace it can take before the stylus blinks, and so it calibrates the most gauge range that each stylus will tolerate. You can override to use a smaller gauge range if you wish. Additionally, you can set a recalibration interval, which is particularly helpful for instruments that are used between many different operators or are in a shop floor environment. So you can say after 24 hours, gauge needs to be recalibrated, otherwise we can't take a measurement. Now, once we've done the calibration, we're left with a residual graph showing the residual form error, and then PT showing the profile error after the calibration. Additionally, for those customers with a rotary stage, we have a rotary access setup built into the manual control. What this allows for is the measurement on many different angles without needing to recrest each time. So this rotary calibration is done on a single part. It can be any optic. It can be a calibration ball. We set it on the rotary stage. The system will automatically crest in 3 different rotational positions, and then remember the spindle XY position in the software. So this means after the initial crest, we can measure many times at different rotational positions without needing to recrest. Now we're going to transition over to the admin side of the software, how these programs are set up. So as I mentioned earlier, the PGI Optics software measures based on the optical prescription of the part. So when defining a new part, we program around the aspheric equation, entering the base radius, conic constant, curvature, whether the part is convex or concave, and then the clear aperture of the optic. We can then enter our aspheric coefficients. Right now showing only the even coefficients. We can show odd, and we can go up to 40 coefficients if we want to. These can be entered manually with the number of digits there are. We also made it easy to import results or import coefficients from other sources, such as a DCOF file, .design file, .coefficients file, .asp files. So many manufacturing equipments allow for the exporting of these designs in one of these formats. So that way you can just use this shared file between your manufacturing system and the software and ensure that you're measuring with the same shape that you've manufactured with. Addition to these aspheric coefficients, we've also included support for diffractive components, where we can use a .diffractive file, and that can be defined in AEU or other optical surfaces. And through AEU, we support diffractives defined in many different manners. On the right, we have a simulator. So once we've entered this coefficient, we can see a simulation of the part shape. And this is helpful to make sure we've entered all the coefficients correct and that the sag of the part is correct. So for example, I've entered 5 millimeters, and it's checking what my sag is at that distance. In this case, it's negative 0.67 millimeters and the slope angle of 15 degrees. This allows you to check to see the slope at different points, compare this value back to your sag table to ensure that your coefficients are entered correctly. With this setup, we have a suitability checker. So this icon will check to see if this measurement is suitable, this component is suitable to measure using the stylus we have loaded in the software. So it checks for stylus blanking. As we can see, we have the slope angle. So if we have a 90-degree cone, it'll make sure that the slope is not more than 45 degrees. It'll make sure that the stylus doesn't bottom out. And in the case of a concave component, it'll make sure the gauge body itself doesn't hit the optical surface. Additional feature to the programming is error checking while we're making the program itself. So these fields have checks built into them. In this case, I have 0 entered for my base radius, my clear aperture. They're highlighted red, showing that this is not a valid value. My base radius must be positive, and the clear aperture also must be greater than 0. And there's a red box around the section that has the error and the box itself. When we hover over here, such as this box, we can see that there's a tooltip explaining what's wrong. Once we've defined the part, we can now define our measurement scheme. We have different measurement options, cresting options, leveling options, and then post and pre-measurement position. The main measurement option stems back to the multiple angles with a rotary stage. So do we want to measure at a single angle or multiple angles? At multiple angles, we can use uniform spacing, set the number of traces and it'll define the spacing, or vice versa. We can also use non-uniform spacing and set the spacing between them. We can establish our measurement length. This can always be shorter than the clear aperture we've previously entered. And the traverse movement will tell us the full distance the traverse moves from one end to the optic to the other end. In this case, I have a run-up distance of 0.3, so the traverse moves 0.3 millimeters, accelerates for 0.3 millimeters before measuring the 15 millimeters, and then deaccelerating another 0.3 to total 15.6 millimeters. And the software will always check that the traverse movement is less than the clear aperture. So you can program your clear aperture to be much larger than the optical component, and then adjust your measurement length accordingly. So that way you have flexibility going forward to change your measurement length. Now with that, we've made some improvements to the control software so that we can have smaller run-up distance, that acceleration period before and after the trace. So this enables us to measure even smaller optics. So we can now measure a run-up distance as small as 50 microns, and that means we can capture as much of the clear aperture as possible. So we can do optics around 1 millimeter in diameter because of this. With a run-up distance of 0.3, and you say you have a millimeter optic, you would only be able to capture 0.4 millimeters of the 1 millimeter clear aperture. With the smaller run-up, we can of course capture much more distance. And as a measurement setting, we can choose if we want to level on any surface. So if we have an optic with flats on either side, or if we have an optic that's embedded to a wafer surface, we can measure on either side of the optic, such as in this shape here. We can measure on either side of the optic to capture that surface So that way we can find out what the tilt of the optical surface, what the tilt between the aspheric axis and this land is. So with the part cresting, we have options for X, XY, XYX, YXY. But we can also, that traditionally uses a best fit arc to find the highest or lowest point. There are some optics, such as this gold one shown here, where there are many high and low points on the optical surface that the software could interpret as a, as a cresting point. In this case, there's 1, 2, 3, 4, 5 different points that the software could interpret as a crest point. We can prevent these false flags or these false finding of crests by using the part design in the cresting. So as we take a crest measurement, it'll compare it back to the optical prescription and see if, and determine where the true crest of the part is. And this helps align optics such as gold ones much more accurately. Additional option is we've now added pre and post measurement positions. So once we've finished measuring the optic, the software can automatically move up and away from the system. And so that way the operator knows that the part is done measuring. And excuse me. So that way we know that the part is done measuring and the stylus is clear from the optic, so it's safe to remove the part without the stylus being safe to remove the part without risk of hitting the stylus. We can also have a pre-measurement position where we can have the stylus positioned close to the crest of the axis, so we can joystick it down closer, or we can just have it automatically move to the start location. In the part programming, we have analysis settings built in since we have analysis directly in the PGI Optics software. And additionally, if you're using the AAU analysis, these settings will automatically apply to AAU when you open it. So we can choose how our radius is applied. Is it applied base radius? Is it least squared? Or is it bounded by the upper and lower limits of the radius tolerance? If we choose to analyze with Talymap, we can set a predetermined Talymap template by pointing to it through our folder system. We can also enable a spike filter, the width of our slope band, and our lambda S short wavelength filter. So the spike removal is particularly helpful for optics that may be dirty at the time of measurement or an environment that has dust, for example. We can set characteristics of a spike and have those automatically removed. So that way a spike doesn't drive the form error of the part. Now we offer AAU as an additional analysis utility. Not why it's called AAU. The Aspheric analysis utility AAU is used for further analysis, and many customers are familiar with using this in the past, so we still support this software. It allows the analysis of aspherics, diffractives, and now additionally Fresnel lenses. So we get the analysis with AAU. In this case, we have an aspheric trace that allows for the form removal. In this case, we get the radius optimized, and we get all the parameters we had in PGI Optics, and then some more. A helpful feature with aspheric optics is we have this X offset, which is used for correcting the offset of our diamond turning tooltip. We can do an additional analysis where we can simulate the X offset being removed and show what the form error of the component would be if that X offset were corrected for. So that way we can see if correcting the X offset would push the part into tolerance or not. We have support for diffractive analysis. We accept polynomial, code 5, Zmax type coefficients for diffractives. And as we see in this analysis, it's removed the diffractive steps. And so we're looking at the underlying aspheric form, or in this case, the residual form after the diffractive steps are removed. And there's an exclusion zone, so the areas immediately around the diffractive step are excluded in the analysis. So we can look at our residual PT, and then we can also look at a table of our diffractive parameters. So our design half diameter, the actual half diameter, the half diameter diffractive, the edge length, the edge radius, zone height, total height, etc. for all of our different zones. In a similar fashion, the Fresnel analysis additionally removes the Fresnel steps, so that way we can look at the underlying base form error. And this Fresnel analysis allows for equal height and equal width settings for defining Fresnel steps with the polynomial coefficients. And we get a similar table of Fresnel step parameters, which is our half diameter, design half diameter, actual half diameter, etc. And lastly, AEU allows for derived coefficients. So as I mentioned earlier, a PGI system you can always joystick it to where you want to measure, tell it to measure, and it'll capture the data even not knowing anything about the surface. So using derived coefficients, we can measure an optic that we don't know the prescription of, and then we can derive the coefficients using different settings. So we can have it find the best fit radius and then the best fit aspheric coefficients. We can do our even coefficients. In this case, I have 2, 4, 6, 8, and go all the way up to A of 20 for that. And additionally, this is just with Asphere. We also have this derived coefficient analysis for aspherodiffractive analysis, for aspherodiffractives. So we can optimize both our aspheric and diffractive parameters to determine the profile of the surface.
Thanks, TJ. So now I'm going to invite our business development manager, Neil, to join us. I can see there are a few questions, and I will ask him to answer all your questions. Okay, Neil, just give a minute. I'm going to send you live.
Okay, thank you, Alice. Right, first of all, you have to excuse me. I'm obviously doing a working from home thing at the moment, so not the best background. However, yeah, so thank you very much for listening in to TJ's presentation. Hopefully you found some of that interesting. Maybe there were some things in there you didn't realise the PGI Optics could do if you already have one. Obviously, following on from this, we'll go through questions now. But if you've got more specific questions about anything you've seen, or you really want to know more about it, obviously always contact our local sales engineers or our area of applications engineers. We have a lot of them all around the world that are very qualified and more than able to support. So yeah, just going through a couple of the questions then, and thank you for writing them and waiting for the responses. One of them here is asking about if you can import diffractives and whether you can, when you import diffractives, can you import that as an image or as an array of heights, and what sort of resolution can we get with that? So when we measure, take any measurements or do any analysis, we rely, for the 2D analysis, we rely on the actual design of the optic. So if we were measuring an asphere, for example, we would put in the aspheric design with the polynomials, which defines the shape for the actual component. We measure it and then we look at a difference to that. It's the same thing for the diffractive. So if you want to measure a diffractive, we rely on having the design as a equation, or in the equation based form with the polynomials for both the aspheric form and then the diffractive form as well. Unfortunately, we can't at the moment take in a simple profile, if you like, that might be generated as a 2D text file and use that as for the basis of the analysis. We do have a separate utility in Talymap or Talyprofile where we can take in a DXF and we can do a comparison to that. But what I would say is when we're analysing diffractives and aspheres, the accuracy of the analysis is very much based around how accurately we can define the axis, literally, of the asphere or the diffractive, and therefore if we can't define the axis and level the form correctly, then we won't get an exact analysis, which is one of the reasons why we rely on a more maths-based algorithm to get the accurate analysis. So hopefully that answers the question there. In terms of, I think that relates to the resolution. We don't term the resolution of our PGI in terms of pixels. We call it in terms of data points along a 2D profile. And the maximum data points we can go down to every eighth of a micron, so 125 nanometers, which is pretty high for us 2D data spacing. Okay, let me just go on from this. Oh, okay, Dan. No, I see. So, well, do you know what I would say here, Dan? It's probably worth, if you want to give me a shout separate to this, maybe we can have a chat separately as to how we could look at handling what you're saying there about whether you're looking at a more shape-based design than an equation-based design. I think that would probably be good, because I feel this could be a conversation that goes on for some time. So yeah, so if you I think, Alice, we've got contact details at the end. We got given out contact details, so if you use those you can get in touch through that, and then we can chat more about that in detail, I think, if that's okay. Okay, I've got a question here. Again, this is about analysis difference between the AAU and when you're reducing the aperture on a measurement, okay, and where you get different radii. Again, this is more of an applications question. Just off the top of my head, depending on the form error that you've got on the actual surface, that can alter the radius that will fit to. I mean, that's a very global assumption, and it very much depends on, as I said, on the what I should have said, on the relationship between the form error you have and the radius that you're trying to fit, and the aperture over which you're fitting it. Now, if you're seeing and you've got a question, if you've got a question about that, again, that's probably something that we should. I'd be interested to see the data that you've got, look at that with you, and then we could have a look at that. So if you contact me separately at the end of this, if you send your email address in this, then we can get back to you again, and we can follow that one up. So I'm sure we can help resolve it or understand where, if there is an issue, what we can do. But to my knowledge, typically any changes in radius will be down to the fitting and down to the form that we're trying to fit. Okay, so hopefully we can take that one offline. I've got another one which is quite good. I didn't expect to get so many questions, so this is good. This is good. What's the biggest part that we can measure on a PGI optics? That's a very good question. On the optic systems, previously we only went up to a 200mm long traverse unit. What we actually have now is we've extended that now, so we can measure up to 300mm, which obviously gives a significant amount of increase in measurement length, and it starts to move into the realm of the larger diameter optics that we're seeing more. Obviously, the depth or the sag that we can measure is very much dependent on the stylus you use, and that relates to the accuracy. But as I've said, we can go up to 300mm. So let's just see. So just bear with me a minute. scroll down and see what the other. Okay, so next question is, yes, we can upgrade from a PGI. If you've got an existing PGI with a 1240 or an running Ultra or an 840 running Ultra, we can upgrade that. Again, have a chat with your local sales engineer to do that. That's not a problem. Just trying to think if we've got any other. Sorry, I'm just struggling to keep my cursor on the scroll down bar here. Excellent. Okay, and I think the last one at the moment is 3D astigmatic analysis. TJ touched on that. Someone's asked the question, can you do it without motorized stages? The answer is quite simply yes, you can. That's not a problem at all. Again, we can, the software is actually designed so that even if you have no motorized stages, just manually rotating the part and recresting every time will allow you to collect the radial profiles, and from that we can generate a 3D astigmatic plot as a 3D surface, or it's just combined 2D surfaces. So you don't necessarily need the full motorized stages to do that. Obviously the motorized stages make it easier, but there's certainly an option there. So yeah, I think that's, just let me check again. Yeah, I think that's pretty much the questions at the moment. So if any of you have any further questions after this webinar, then you're welcome to contact us. You know, go through the Taylor Hobson website. You can get our contacts through there, or go to your local sales guys, applications engineers, or if you've got my details, contact me directly. We're more than happy to help. So thank you for listening very much. And hopefully you got something from this, and maybe we'll hear from you again in the future. Thank you.
Okay, thank you. Neil, can you hear? Oh, just a minute.
Okay.